I left my phone down there. I was going to time myself. Never mind. I will attempt to pronounce it, and I'm going to apologise if I get it wrong. I've been practicing. Yeah, my name's Ben. I'm a postdoc at the University of Manchester, and we've been working with the Iceland Met Office looking at satellite-derived SO2 emissions from Fagradalsfjall in Iceland during its 2021 eruption. So the key points I want to nail home at the end of this talk is that we are able to calculate sub-daily SO2 emissions for low-intensity eruptions. As Isabel perfectly showed in the last talk, satellites are really great for these sort of really big explosive eruptions, but we really struggle looking further down in the atmosphere to sort of more gentle and effusive eruptions, and we're trying to see how far we can push it, basically. It turns out we can. Hey, this can be applied in a relatively automated fashion, which is good news, and we're pretty confident in the results that we've gotten out so far. And perhaps one of the most interesting things is that we are able to infer details about the eruption activity from these measurements as well. So motivation behind it. The motivation was basically the eruption of the volcano. So it erupted on the 19th of March in 2021, ending about 800 years of quiescence on the peninsula, on the Reykjanes Peninsula in Iceland, which is given by this map here. Now, sort of from the historical data, these eruptive periods typically last about 200 to 400 years. So this could be the beginnings of quite a long-lived sort of volcanic activity on the peninsula, which is quite important because gas emissions from these eruptions can be very hazardous by degrading local and regional air quality. But from the more monitoring side as well, the amount and ratios of the gases that are being emitted reflect the magmatic system, so they can tell us about the volcanology that's happening under the ground. And why is it important here? Well, Reykjanes is home to about 70% of Iceland's population, and a good chunk of its infrastructure as well, including airports and geothermal plants. So if this is going to be volcanically active in the future, it's good that we can know that we can monitor these eruptions in good detail. To give you a bit of an overview of the eruption, it was quite a dynamic one, and it was split into sort of 5 phases. We start with phase 1 and phase 2, which is from the 19th of March to the 27th of April. This was sort of quite weak effusive activity, starting from 1 vent and spreading to I think to a maximum of 8, which is generally sort of quite low-level effusive activity with lava emission as well. We then move on to phase 3, where there's quite a significant uptick in the activity, so become a lot stronger, sort of lava fountaining, and quite sustained emissions coming out then. This then sort of morphed again into phase 4 at the end of June, where we sort of see much more periodic activity, where we have maybe 12 or 24 hours of quite intense activity, eruption, followed by 12, 24 hours of basically cessation, and that sort of on off occurred for a couple of months. And then finally we had phase 5, which had this sort of week-long pause of eruption where everyone's like, oh, has it finished? And then it wasn't. Hey, it's back for another week, and then it did finish. So yeah, lots of different eruption styles, lots of different eruption strengths. So this was the perfect test bed to really sort of test our analysis of this. Combined with the fact that the Icelandic Met Office were doing lots of very in-depth measurements of their own to compare our measurements with. So to give you a bit of an overview of the measurements, we're using a UV instrument called Tropomi, and this gives us a daily snapshot of the SO2 in the atmosphere. So this animation is just showing you the plume every day. So the darker colours here are showing more SO2. I think we sort of synced colour schemes with me and Isabel, so quite thankfully there. So, and you see that as we go through time, we have much more strong emissions, and then this sort of drops off and becomes a lot more sporadic. You'll be able to see in a second. The eruption itself lasted 185 days. We were able to detect plumes on 158 of these, so 85%. And we're pretty confident that most of the days there was a plume, we detected it, because the ones that we missed were either sort of first and last day of the eruption or during these pauses or pulses of activity. But just knowing where the SO2 is in the atmosphere doesn't give us an emission rate from the volcano, and that's what we're really interested in. And for this, we need to know the altitude of the plume and also the time and altitude at which it was emitted from the volcano. No, don't go again. So how do we get from our daily SO2 emissions to our daily SO2 imagery, to emission rate? Well, so we use this thing called PlumeTraj, which is a back trajectory analysis toolkit, where we launched a series of back trajectories using HiSplit, which is a sort of a trajectory model, from pixel locations in our plume at a range of different altitudes. And because of wind shear in the atmosphere, these go woo. So high altitude ones will go one direction, low altitude ones will go the other direction, and the altitude at which the plume is at, hopefully, returns to the volcano. And this gives us our plume altitude, which is important for actually measuring the mass in that pixel, but also the injection altitude and time, which means that we can fully reconstruct the emission history of that volcano, basically from this single snapshot image. So we go from a daily image to sub-daily emission rates. And we can produce plots like this, so we get our pixel, our corrected sort of vertical column density, which is sort of the amount of gas in our pixel, and also plume altitude and plume age for each individual pixel in our plume. So we've now got everything we need to reconstruct our emission rate. Oh no, too far. So we can, I just wanted to show you an example of a single day here. So this is actually using data from 2 different days. Our overpass is about 1:30 UTC. So everything to the left of this grey dashed line is measured from the orbit that happened at that grey dashed line. Everything to the right is data that's been measured the following day. And so this is showing a bit of a heat map here. So this is the strength of the emission at the volcano as a function of time on the x-axis and altitude on the y-axis, and the darker colours here are representing a stronger emission. And on the top, we've just summed it all up to give our total emission rate, and on the left here, we've sort of summed the total emission for that entire day. We can see that it's quite variable with time, and also that to the left, where we've got our younger pixels, so the plume that was emitted just before our overpass, our emission rates are generally higher than the really old pixels that were emitted way before our overpass. And that's just because as Esse2's reactive gas in the atmosphere, eventually it diffuses and is chemically processed out, so we lose our ability to see it. So we generally are looking at the peak values for each day as our sort of closest to what is the truth. And we also compared to some of the ground-based measurements on this day. So the triangles on this sort of colour map here are from visible cameras that were looking at the plume, sort of plume top and bottom. You see that these tracked really nicely with our altitudes throughout this day. And equally, we also looked at ground-based mobile DOAS traverses of the Esse2 flux that was coming out. And although they don't agree at the time, as I said, the really old stuff is generally an underestimate, and they agree pretty well with what we measured just before the overpass time. So we're really happy with how this is working. And we roll this out for the entire eruption. And you can see this, as with the phases, it's quite dynamic. So we have some weak stuff in phases 1 and 2 and phase 5, very strong at the beginning of phase 3, and then it sort of peters off a little bit. And then we have very sort of sporadic measurements through phase 4. Again, we can compare to our camera data, and we see we have really quite excellent agreement with those camera altitudes. I think this is one of the coolest things about the study, and that we're looking at plumes very close to the ground, where these sort of global meteorological models don't work so well, and yet we're still able to get really good, we're really well nailing the injection altitude, which is a really important factor for predicting where that gas is going to go for predicting air quality. There are some outliers, and most of these are due to errors in the wind field. As I said, it's very close to the ground, very small scale, so it's not perfect, but we are capturing the majority really well. When comparing with the emission rates through time, you can see that our agreement is much less good. We get good agreement during this sort of high activity phase and the beginning of phase 3, but apart from that, we seem to be a little bit all over the place, which is not so surprising when we're looking at, especially in Iceland, it's very low altitude plume. It's very cloudy, it's quite difficult for satellites to see, so it's not necessarily surprising that we're not able to capture the full emission rate during the really low stuff, but we are able to catch when it's a bit better. Some of the discrepancy during this sort of pulsating activity is mostly due to the fact that it depends whether we're capturing the plume at the same time as the traverses. So sometimes the traverses will be capturing an on phase and we're an off, or we're capturing an on and they're an off, or sometimes we line up and they match too. So it's a bit hit and miss as to the timings of the measurements in those cases. And we also looked at the lava effusion rate, so that's the orange in here, and we can see that those line up quite nicely with our measurements actually. So we get higher effusion rates during times where we have higher emissions, which just makes sense. We were also looked at the cloud fraction, so we were quite aware that cloud does block our ability to see Esse2, but there's no sort of clear relationship with the cloud fraction, which is quite reassuring for us. So it shows that the cloud isn't having a major impact. But we wanted to dig a bit more into what is actually causing the discrepancies in the emission rates. So this is 3 of the same scatter graphs, each coloured differently. So on the y-axis, we've got our plume charge, our trochonium emission rate, and on the x, we've got traverses. And you see there's sort of 2 populations, one which they roughly agree, and then another one where they don't, and then there's this one outlier up here. And we looked at both cloud fraction and injection altitude, and we can see that although cloudier days and lower injected altitude days there's a few clustering down here, but there's definitely no systematic sort of explanation as to what's going on. When looking at the phase of the eruption, we can see a little bit more information. For the weaker phases, so 1, 2, and 5, they're mostly clustered down here, where our plume charge is underestimating compared to the traverses. The strong phase in phase 3 is basically all agreeing with each other within our error estimates. And then in the sort of pulsating stuff in phase 3B and 4, so I should say I split phase 3 into where we sort of had that drop halfway through phase 3 on the 25th of May into 3A and B. So the more pulsating stuff, it's sort of more in phase 3B and 4 is, as I said before, a little all over the place depending on which part of the plume we're capturing. We also want to look actually what is the relationship between the cloud altitude and the plume altitude, and is it basically the fact that we can't measure it when the cloud is on top of the plume because we can't see through clouds so well. And we found that this isn't the case. So this is just a plot of the difference in plume altitude to cloud altitude. And you can see that the plume is typically coming in about half a kilometre or more above our cloud. And the fact that this is roughly symmetrical, this shape, is quite reassuring because that says to me that we're not losing too much gas below our cloud. There is a jump at 0, which suggests we are losing a bit, but I think the bulk is coming through okay. So we're very happy with our results. So sort of take home points, we're able to reconstruct the S2 emissions for the entire eruption with really good agreement between the ejection altitude, which is really reassuring for future eruptions so we can better monitor the gas dispersal, and sort of variable agreement with the emission rates. But we are seeing quite systematic changes in the emission behaviour with changes on the ground in the eruptive activity. The best agreement we get, sort of non-surprisingly, is when we have really strong and steady emissions where we're definitely measuring the same thing. And sort of somewhat excitingly, okay, Fagradalsfjall was a really well monitored on the ground eruption. Not all volcanoes are like that. There's many volcanoes around the world that don't have that ground infrastructure to really monitor that well. And I hope this shows that we're able to roll out that same analysis to volcanoes globally, and also potentially in the future in near real time, as both the satellite and meteorological data are available the same day, so we can do this analysis. And this is something we're currently working on. So if anyone wants SO2 fluxes for their volcano, please get in touch. I'm sure we can sort that out. So thank you very much.